Hey everyone, welcome back, and today let's solve Leetcode problem 2017 titled Grid Game. So we're given a zero-indexed 2D array grid of size 2 by n, where grid at index r index c represents the number of points at position rc on the matrix. Two robots are playing a game on this input matrix, where both the robots initially start at index 0, 0, which is the uppermost left cell, and want to reach 1 n minus 1, right? And that would basically be this cell right here. It would be the rightmost bottom cell. Okay, so each robot may only move to the right from RC to RC plus 1, or they may move down from RC to R plus 1C. And at the start of the game, the first robot moves from 0, 0 to 1 n minus 1, collecting all the points from the cells on its specific path. And for all the cells RC that robot actually traverses on that path, that specific cell grid at RC would then be set to have a value of 0. And then once that first robot actually completes its path to the rightmost bottom cell, then the second robot will then move from 0, 0 to 1 n minus 1, in that case collecting the points on the path. And note that their paths may intersect with another, basically meaning that there would be a chance that the second robot would get some zeros in the cells that the other robot already traversed on in its previous first path. So effectively in this problem, the first robot wants to minimize the number of points collected by the second robot, and in contrast, the second robot wants to maximize the number of points that it collects. And so if both the robots play optimally, meaning best as possible for their specific constraint, we need to return the number of points collected by the second robot. So that's very important to note, not just the first robot or in general, but rather the number of points optimally collected by the second robot. Right, which keep in mind, its goal is to try to maximize the number of points it gets. So in example 1, we're given a matrix. In this case, we're given a red path and a blue path. Basically, the red path would represent the optimal path of the first robot, and the blue path would represent the optimal path from the second robot. Okay, and in this case, let's talk about why our output is actually 4. So this is the path, the red section, that the first robot actually takes. And so on all of the cells that it traverses, every single cell that this first robot hits would be set to 0. So this 2 would be a 0, this 5 would be a 0, this 5 would also be a 0, and this specific one would be a 0 as well. Basically, all the cells that the first robot traverses in its initial path. And once this first robot is done traversing the matrix, then the second robot comes into play, starting at index 0, 0, or cell 0, 0, and then it tries to maximize the number of coins in its path, going from this cell to the rightmost bottom one. Right? And in this case, we see that this 2, this 5, and 1 would all be set to 0, and so the most optimal way or path for the second robot to take is actually also highlighted in blue. Basically, he goes right, right, and then down, and that would be a score or path value of 4, because of course it collected exactly one cell in its path that wasn't set to a 0 from the first robot that had a number of points cell value as 4. Right? So the second robot would collect technically 0 plus 0 plus 4 plus 0 points, but that really just simplifies to 4 points, which is the optimal path to maximize the number of points that the second robot took, and so that would be an output of 4. In example 2, we see that our 2 by n matrix is going to be 3, 3, 1, 8, 5, 2, and 0, 3, 1, 0, 0, 0 for the first and second robot paths respectively. Why does this output also have a 4? Well, let's think about it. If the first robot is playing optimally, look at how he's greedily taking all of the cells with larger values, right? As you can see, this robot goes from 3 to this 8 to this 5, and 5 to 2, right? Basically setting all of those cells to be equal to 0. And the second robot is trying to maximize or make his number of points as high as possible. And so instead of going through this path with all zeros, he goes from the 0 to this 3 to this 1, then this 0, as the most optimal path that the robot can take. And so in that case, he'd have a score or number of points value as 3 plus 1, which would also be 4. Keep in mind, these are both the most optimal paths taken by both the first and second robots in red and blue as well, right? In example 3, we have a little bit larger of an input here. We see that we have 1, 3, 1, 15, and 1, 3, 3, 1 as our input matrix. And in this case, our output as such, or our maximized number of points for the second robot would be 7. Right, because as you can see, the optimal path for the first robot would be highlighted here. We have 1, 3, 1, 15, 1, setting all of those specific cells to be equal to 0. And from all the other cells that robot can actually traverse for the second initial path, that second robot can go from the 0 to this 1 to this 3 to this 3 to this 0. Technically, the second robot could have also went from these cells as well, but since they're all set to 0, that wouldn't be optimal, and that would basically be minimizing its number of coins. In this case, we want to maximize the third robot's coins, and so it's going to take 0, 1, 1, 0, 1, 3 plus 0 number of points, which would simply be 6 plus 1, or 7 points optimally. So for the constraints here, we see that the length of the grid basically telling us that the number of rows in the grid is always going to be equal to 2 by some dimensions n. Basically, n would be the number of columns we have. And we're also given that that n value is not going to exceed 5 times 10 to the 4th power, which, keep in mind, is pretty large, especially for runtime and memory or space-time complexities as well, which is something that we should keep in mind, because that really tells us that worst case, we can really have a big O of n solution, right? We can't really have n log n, let alone n squared, and so big O of n or log n would be kind of the runtime complexity to chase of to make our solution efficient for these specific time constraints, right? And we're also given that grid at any index r, index c, basically any cell value is not going to exceed 10 to the 5th power, and is going to be at least 1, meaning non-negative and also not 0. So with the problem statement, constraints, and examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what is one very important observation that we can really make to help us lead to our solution and even solve this problem in the most efficient way possible? Well, that observation is that the player 2's total points, or I guess in this case, the second robot's total points, would depend on the first robot's path. Why is that? Well, because the first robot is always going to block the points, basically setting the cells to be 0 for all the same cells that they actually visit. Right? Because, of course, the problem literally tells us that, right? And another very important observation that we have to really make is that the second robot is always going to play optimally to maximize their points, right? So really, our task would be to be minimizing player 2's points by finding the best path for player 1. Because at the end of the day, player 2 or robot 2's path is going to depend on robot 1's path. And so since robot 1 goes first, we simply have to maximize or find the best path for player 1, because that would tell us the best optimal path for player 2 as well, or robot 2. You can use them interchangeably as well. So for a high-level rundown of the solution, basically, we're first going to pre-compute the prefix sums for both of the rows of the grid, and it's very helpful that we're guaranteed that we're going to have exactly 2 rows for any input, which is very helpful for this problem. And these prefix sums are basically going to help us quickly calculate the total points that we actually collect in specific segments or specific paths on the grid, right? Once we actually pre-compute those prefix sums, we're also going to iterate through all the possible points where player 1 could move either down and split the grid into 2 parts, which would be top right and bottom left, right? Those are the 2 kind of directions that the robot can move in. Either it can go down or it can go to the right cell. And for every single split, we're going to compute the points that the robot or second robot can actually collect in both of the parts, and then track the maximum of those 2 values, right? Because of course, we're trying to maximize the number of points that the robot 2 can actually take, and robot 1 as well. And effectively, we're going to minimize the maximized points, or rather, sorry, we're going to minimize the maximum points that the robot 2 can actually collect. Because again, it all depends at the end of the day on robot 1's path. And so basically maximizing the number of coins taken for robot 1, we're minimizing the maximum points that robot 2 can collect, right? We're literally, for each split, computing the points that the robot 2 can collect in both of the parts, either down or right, and tracking the maximum of those two values, right? So with that little rundown out of the way, let's go ahead and dive straight into the code here. So what I'm going to first do is actually initialize my top and bottom prefix, like I just talked about. So I'm literally just going to call them top prefix and bottom prefix. And what they're going to be initialized is basically a list. And I'm going to be using something called iter tools here. You don't need to do this. We really could just get the sum of basically the bottom and top row very easily for our grid using a simple for loop. I'm kind of just going to make it a little bit more spicy and get that cumulative sum in a different way. Doesn't really matter. Just use a for loop here if this isn't built into your specific language. The way I can do this in Python is to get the list of iter tools, a module in Python, which I don't have to really import because this is a Leetcode editor. And I'm going to use the .accumulate method here. I think this is how you spell accumulate. I could be wrong. Maybe it's accumulate. And for our parameter, we're going to pass in grid at index 0. Right? And very similar logic here. We're going to do this exact same thing for the bottom row, or the bottom prefix, except it's going to be for the first row, technically, or the second row, instead of the initial one. So it's going to be a list of iter tools dot accumulate. Yeah, that should be right. In this case, instead of passing in grid at index 0, we're going to pass in grid at index 1. That would be the cumulative sum for the bottom row, and this is the cumulative sum for the top row. That's why it's very helpful that we're given a 0 index to the array of size 2 by some dimension n, right? We don't know how many columns there are, but we do know that we're always going to have exactly guaranteed 2 rows, okay? And to kind of reiterate what this code really does here, basically what the iter tools accumulate method or function really does that's built in, it basically helps us compute the prefix sums for the corresponding rows, where the top prefix would store the cumulative sums of the top row, which really means that top prefix at index I would give us the sum of the first I plus 1 elements in the top row, and very similarly the bottom prefix would do the same thing for the bottom row. And really the use of these variables is simply going to help us calculate the player 2's points for any split point that we can actually form from any cell, right? So once we actually initialize these two prefix sums as such, now, like I talked about before, let's actually get the min-max points, because we're literally trying to minimize the maximum points that player 2 or robot 2 can collect. So I'm going to literally call it min-max points, and it's going to be initialized to the float of infinity, something that we're trying to minimize, right? Basically, this is kind of like our result variable. It's going to store the smallest maximum points that player 2 can collect, given that player 1 or robot 1 actually plays as optimal as possible. And we're really just setting it to float of infinity because, of course, we're trying to minimize the value in each iteration or for every single split of the input matrix. This is the minimum maximum points that the robot 2 can actually collect. Okay, so now let's actually iterate over all the possible columns, basically iterate over all the possible columns, not columns, that player 1 or robot 1 can actually move down to, right? And actually calculate all those different splits. So the way I can do this in Python is basically for I in the range of the length of the grid at index 0 here. We're going to set the top right for these splits to basically be the top prefix. This is the whole idea why we actually calculated the prefix sums at -1. And what -1 indice really does in Python, basically it gets the last index of an iterable, right? Pretty helpful to know, minus the top prefix at I, right? And what we're really doing here on this line here, we're basically calculating the points that the second robot can actually collect in the top right segment after player 1 actually moves down, right? To kind of reiterate, here we're simply calculating or iterating over all the possible columns where player 1 can move down. And on this specific line here, for this top right initialization, we're getting the basically total points in the top row to the right of the specific column I. Okay, so once we actually initialize the top right variable, let's get the bottom left variable. Similar structure here. It's going to be the bottom prefix instead of the top one at -1, or rather I should say I minus 1. And we can only get the bottom prefix at I minus 1 if it doesn't go out of bounds. So if I is at least 1. We can check that basically if it's greater than 0. However, if I is not greater than 0, we're simply going to default to 0 because otherwise we'd go out of bounds. We can't have negative indices, and so we'd simply go to 0, right? If I is actually not greater than or equal to 1, right? So this bottom left variable, basically it's going to be the total points in the bottom left row, or rather just the bottom row to the left of that specific column I. And very similar structure here, we're simply calculating the points that the second robot can collect in the bottom left segment after the first robot actually moves down, right? And for either of these two splits or segments here, we want to find the maximum points that player 2 can actually collect in these two choices. So I'm literally just going to call player 2 points, or either, for more clarity, I'm going to say robot 2 points. But I hope you guys get the point. It's going to be the maximum of these two specific splits or points gaining, either the top right split or the bottom left split, of basically simulating going down, right? Effectively, top right is basically going to calculate the second robot's points in the top right segment, and bottom left is simply going to calculate the second robot's points in the bottom left segment. Meaning, if player 1 hasn't actually moved down yet, meaning I is actually equal to 0, that means bottom left would also be equal to 0, right? And player 2 points, robot 2 points, I should technically say, basically that's going to be the maximum of those two values because player 2 would optimize to collect the most points, right? Again, I'm using player and robot very interchangeably. Note that they mean the same exact thing. I feel like player is a little bit more, I don't know how to say it. I think player is a little bit more natural to me, okay? So once we actually get to player 2 points, we want to actually update our result variable. That's the min-max points for the player 2 that we actually want to return. So I'm literally just going to call min-max points, and I want to minimize this value, right? We literally want to minimize the maximum points that the second robot can collect. And so I'm going to minimize it by setting it equal to the minimum of course, itself, because we don't want to make it smaller, and the current iteration calculation for this specific split, player 2 points. And I just realized this is actually robot 2 points, not player 2. That is a little bit better. But yeah, we're literally minimizing the min-max points to make sure that the first robot strategy would lead to the optimal, or rather the least optimal outcome for player 2, because that's literally the choice that the first robot would make, and so that's how the second robot's path actually depends on it, because we're guaranteed that the first robot is going to go first. And effectively, once this for loop is actually done executing, once we've actually went through all the possible split points, we're going to return this min-max points because it would have actually represented the best outcome for player 1, and also hence the most optimal outcome that player 1 could make, and what player 2 would eventually be taking the path of, because that would be what player 1 takes. Player 1 is trying to be as optimal as possible, and so this is basically what player 2 would take, as it depends on player 1's path. So we're going to return the min-max points. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. So let's go ahead and see if it works. And as you can see, this is just really just about as efficient as you can really get it to be. So to kind of reiterate how this code actually works as a whole, effectively, again, we're computing the best path for player 1 to minimize the maximum points that the player 2 or second robot can actually collect. And the way we do this on a high level is basically pre-compute the prefix sums for actually the range sum calculations, and then we iterate through each potential split point for all the different splits in the matrix, and calculate the second robot's optimal points for each split, and effectively track the minimum of these maximum points to actually find the optimal strategy for player 1, which is eventually the strategy that player 1 would be choosing, because that's exactly how it actually plays. And we're given that, or guaranteed that, in the problem constraint. So for the runtime and memory complexity, the runtime complexity would be big O of n. It is just a linear time solution where n is the number of columns, right? And the reason why is because we're actually computing the prefix sums in big O of n time, and also iterating through all the columns in big O of n time. And so technically it's big O of 2 times n, but since coefficients and constants don't matter in runtime and memory space complexities, this is just a big O of n or linear time solution. And for the memory or space complexity, it's also going to be big O of n because we are actually using those auxiliary data structures of that extra memory from the top prefix and bottom prefix lists, right? We actually have to store the prefix sums of both the rows. And why is that? Well, because again, The whole idea of prefix sums is that they allow us to actually efficiently calculate the total points in constant time for any segment of the grid. And that would really heavily reduce any redundant computations, and that's what really keeps our solution as efficient as possible. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.